5.1 Systems of Linear Equations, Part 2. Substitution versus addition and elimination method. In Part 1, we practice using the substitution method to solve systems of linear equations, and we also practice using the addition and elimination method to solve systems of linear equations. And by now, some of you may prefer one method over the other, and that's fine. However, I do want you to be well versed enough in both methods so that you can use the most efficient method, right? So using the method that is most efficient will decrease the likelihood of you making a mistake in the problem. So in parts A, B, C, and D of this problem, we are not going to solve, but we're just going to discuss the different methods and how that would work out. So for the system in part A, I see that there is a coefficient of -1 on the y in the first equation, making this a really good candidate for the substitution method. You could easily solve that first equation for y and then plug into the second equation. So the substitution method would work really well here. However, you could use addition or elimination method with this. You could easily take that first equation and multiply by a -2, and then the y's would eliminate. So I think this is a really great problem for substitution. However, if you wanted to do addition or elimination, you could do that as well. All right, for part B, you really should be using addition or elimination method here. You really should not choose a variable and solve for it using the substitution method, especially because we notice that if you add down, the x's will eliminate anyway. So you should use addition and elimination method there. For part C, we notice that what you could do is solve for that x and use substitution because there is a coefficient of -1 on that x. However, you're going to be using some you'll still run into a fraction. So really, what I would want to do is multiply that first equation by 2. If I multiplied that first equation by 2, the 2 and the 1/2, those would cancel, giving me just an x. That would be my new number 1, and then number 2 could stay the same. And then you'll notice that the x's cancel out. So really, at first sight glance, this looks like substitution would be good because of that the -1 coefficient on the x. However, addition elimination method would probably be most efficient there. And for D, well, everyone I think here should be using the substitution method for that. We already have a variable solved for. We know that x is 3, so you just plug a 3 in for that x. Example 1, we're going to solve that system of linear equations, and we're not told which method to use, so we can use whatever method is most efficient. And I claim that the substitution method is most efficient because we already have a variable solved for, y equals. So what we want to do is take that 2 minus 3x and substitute it into the other equation in 1. So if I do that, I get this. So that's what I get if I take equation 2 and substitute it into the other equation 1, where its corresponding variable is y. So now that gives me an equation with x. Let's solve for x by distributing that 2. Combining like terms, the x's go away. And something interesting happens. I was hoping that I would get x equals some number, but the x's went away. So this is a unique scenario, and this is the scenario that is when the variable that I'm solving for goes away. And always, whenever that happens, I want to ask myself one question, and that question is, am I left with a true or false statement? I am left with a false statement. So what that means is that there is no solution. Now, so that answers the question, no solution. That would be the answer. However, let's expand this a little bit more. Recall from the beginning of the part 1 video, no solution occurs where the lines are parallel because solutions are where lines intersect. So if there are no solutions, then there are no points of intersection, which means that 1 and 2 must be parallel lines. So I see that number 2 is y equals negative 3x plus 2. It has a slope of negative 3 and a y-intercept of 2. Let's look at number 1. I'm going to solve that for y equals mx plus b so I can compare it to number 2. So now if I divide everything by 2, I get this is in y equals mx plus b form, so now I can say that the slope is negative 3 and the y-intercept is 7 over 2. So this confirms that the two lines are in fact parallel lines. They have the same slope, but their y-intercepts are not the same, so they're not the same line. Therefore, no solution. Example 2, we're going to solve this system of linear equations. We're not told what method to use, so we can use whichever method we want or is most efficient. And I believe that the substitution method is most efficient because we already have a y solved for. So I can take that y and plug it in to the other equation where the corresponding variable y is. So if I do that, I end up with this. So I take the y from equation 2 and I plug it in to the y in equation 1. And that gives me an equation with just x. I'm going to solve that for x, so I'm going to distribute the negative 3. Combining like terms. So the same similar thing happened in this problem, example 2, that happened in example 1. The variable that I was solving for, x, went away. So what I want to ask myself is, am I left with a true or false statement? Well, I'm left with a true statement. So that means that there will be an infinite number of solutions. And that would be my answer. Let's expand on that. Let's look at these. I know that for number 2, we have y equals 3x minus 4. The slope is 3, and the y-intercept is negative 4. Let's take a look and see what number 1 looks like. So we're going to solve number 1 for y equals mx plus b form. So I'm going to divide everything by negative 3. And I see that the slope is 3 and the y-intercept is negative 4. So if I compare those, I notice that they're the same. They're the same lines. So we say that they are coinciding lines. And these are the same lines, so they intersect at an infinite number of places, which is why the answer is no solution. I'm sorry, is infinite solution. Example 3, we are going to, this is an applied problem, so that means that it's a word problem, it's an application problem, and we're going to need to create a system of linear equations and solve that in order to answer the question. So here's the problem. A bank teller has 48 bills, and those 48 bills are a combination of $20 bills and $5 bills. So I don't know how many $20 bills there are, and I don't know how many $5 bills there are, but there's a total of 48 of them. The value of those 48 bills is $405. The question is, how many $20 bills does he have, does the teller have? All right, so the first thing we're going to do is define our variables. So our variables will be x equals and y equals. And we want to define our variables in such a way where if we solve for one of them, it would answer the question being asked. And the question is, how many $20 bills does the teller have? So the question is, how many $20 bills? So we're going to let x equal just that. So we're going to let x equal the number of $20 bills. Because now, if we solve for x, then that will answer that question. There's also $5 bills in this problem, so we're going to let y equal the number of $5 bills. And we'll solve for x, not y. Now we're going to create a system of linear equations, and a system of linear equations will be something plus something equals something, and something plus something equals something. All right, so on the right-hand side of those equal signs are total amounts. So if I look through all of the quantities given to us in the problem, I see two numbers that are totals. 48 is the total number of bills, and 405 is the total value of those bills. So the total numbers go on the right-hand side. Now, I noticed that one of those totals has a unit of measure, dollars. So all of the quantities in this second, the bottom equation, should also be dollar amounts. Well, the dollar amounts are 20 and 5. 20 we associated with x, and 5 we associated with y. So this would become 20x plus 5y should equal $405. Now the top equation equals 48. 48 is the number of bills. I don't know how many bills we have. I don't know how many $20 bills we have, and I don't know how many $5 bills we have, but I know that total of them we have 48. So our system of linear equations should look like this. And we want to find x because we assigned x with $20 bills. All right, so we can solve this system for x however we want. I'm going to use the addition and elimination method. If I want my x's, if I want to find x, then I don't want to eliminate x. I should eliminate my y's because I'm solving for x. So in order to eliminate the y's, I'm going to multiply equation 1 by -5. So here's what I get if I multiply that first equation by -5. 48 times 5 gives me -240. So that's my new equation number 1. And then 2 will stay the same. All right, so that's my new system. So now I'm going to add down. $405 minus 240 gives me 165. I'm running out of room, so I'm going to finish this up here. So I have 15x equals 165. Dividing both sides by 15, I get 11. So the question was, how many $20 bills does he have? He has 11 $20 bills. Break-even analysis. So this last objective is we're going to use a system of linear equations to analyze where we break even. So let's first explain let's go over the break-even analysis, and then we'll do a problem. So with a break-even analysis, if we break even, that means that the profit we make is 0. We're not making any profit. The money going in is the same as the money coming out. So we have two types of functions for money coming in and money coming out. The cost function is represented by C of x, and it is the fixed cost plus a variable cost. So a fixed cost is going to be an amount of money that is not, that it's going to cost us, like we have to pay for this, but that money is not dependent on the number of, for example, widgets we produce. So say if we're producing widgets. You know, of course, each widget that we produce is going to cost something just to produce that widget. So that's the variable cost. So the cost per unit produced times X. So that's the variable cost. But in addition to that, we also have to pay for maybe lights to keep, you know, the place on. Maybe we have to have payroll and, you know, health insurance, things like that. Those are fixed costs. So the cost function will always be fixed cost plus variable cost. The revenue function is how much money is coming in, and that is R of X, and that's how much we make. So that is definitely a dependent upon the number of widgets we sell. The more widgets we sell, the more revenue we're going to make. So the revenue function, R of X, is the price per unit sold. And since it's per unit, it's going to be times X. Anything where it's per unit should be times X. Now the break-even point is the point where the cost function and the revenue functions are the same, exactly the same. So the cost function is usually will go down with the number of widgets that you make because you get the method, things get more efficient. And then the revenue function usually increases. The more widgets you sell, the more money you're going to make. Now, in the real world, these might not be exactly lines, but we're keeping things simple here. So this is the revenue function, and this is the cost function. And then the break-even point is where it's a point in two-dimensional space. It's where the cost and revenues are the same. Now this is a point in two-dimensional space, so it has an X and a Y coordinate. X equals is the number of units, or the number of widgets. Y is going to be the amount of money coming in, how much we make, which at the break-even point is the same as the amount of money going out that we're spending, our cost. Example 4. So this is an application of the break-even problem. We produce bicycles. We have a fixed cost of $100,000, and it costs us $100 to manufacture each bike. We sell each bike at $300 each. So we're going to analyze that. So we're going to write the cost function, C of X. Well, the cost function is always fixed cost plus variable cost, and variable cost is dependent upon how many units you're making, so that's going to be at times X. The fixed cost is the cost that is not dependent on the number of bikes, which is $100,000. The variable cost per bike is $100. It costs $100 to manufacture each bike, so that's 100x. So the cost function, C of X, is 100,000 plus 100x. The revenue function, R of X, is how much we sell each bike for. So it's the amount that we sell the bikes for per bike. It's per bike, so it's going to be times X. Well, we're selling the bikes for $300, so that's $300 per bike. Per bike means times X. So the revenue function is 300x. Part C, we're going to determine and interpret the break-even point. Okay, well the break-even point occurs when the cost function and the revenue functions are the same. So I'm going to set them equal to one another. So that's what it looks like if I set the cost function equal to the revenue function. And now I want to solve for x. So if I subtract 100x from both sides, I get now I'm going to divide both sides by 200. And 100,000 divided by 200 gives me 500. So x equals 500. So that means that in order to break even, we need to manufacture and sell exactly 500 bikes. Well, so now we're going to, the break-even point is a point in two-dimensional space. So it has an x coordinate and a y coordinate. The y coordinate is the amount of money going in and coming out, which is the same at the break-even point. So the money coming in and coming out, so the y coordinate is going to be C of 500, or it will be R of 500, because recall that at the break-even point, 500, the cost and revenue are the same. So I can calculate either one of these. I'm going to calculate both of them just to show you that they are in fact the same. All right, so right now I'm plugging 500 into my cost function. And down here, I'm going to plug 500 into my revenue function. And so if I do 100 times 500 plus 100,000, that gives me 150,000. And this is dollars. And then 300 times 500 is also 150,000. So you can see that at 500, that's the break-even point, and that ensures that the cost and the revenue are the same. So that's determining the break-even point. Determining the break-even point says that X, we need to produce 500 bikes, and then to interpret that, we're going to say if we produce 500 bikes, then we will make 150,000, and it will also cost us 150,000 to do that.